Periodic trends. There are a number of properties that correlate with an element's position in the periodic table. Although it is never an explanation for the difference in properties to say something like, element A is further to the left in the periodic table. To explain the differences in these properties, we use two principles. These two principles can be used to explain observed trends in sizes of atoms and ions, ionization energy, and electron affinity. These two principles are 1. The nuclear charge, or the effective nuclear charge. 2. The increase in quantum number as the valence shell increases. In a many-electron atom, electrons are both attracted to the nucleus and repelled by other electrons. The nuclear charge that an electron experiences depends on both factors. As the diagram shows for sodium, the inner electrons, also called the core electrons, shown here in orange, spend most of their time closer to the nucleus than the outer or valence electrons, shown in blue. As a result, they effectively shield the outer electrons from a significant portion of the charge of the nucleus. The effective nuclear charge, symbol for which is Z sub EFF, is found this way. Effective charge equals Z, the atomic number, the number of protons in the nucleus, minus S, a screening constant, usually close to the number of inner or core electrons. In the case of sodium, the effective nuclear charge is 11, the atomic number, minus 10, the number of core electrons, or plus 1. When we are dealing with elements in the D block or F block, the D or F electrons are considered core electrons. The effective nuclear charge, and the nuclear charge itself, for that matter, varies across a period, but does not change going down a group or column. You should confirm for yourself that all of the alkali metals, for example, have an effective nuclear charge of plus 1, and all of the halogens have an effective nuclear charge of plus 7. The effective nuclear charge and the nuclear charge increases going across a period from left to right, and can be used to explain trends that operate across a period. Effective nuclear charge cannot be used to explain trends within a group. To explain trends within a group, or column of the table, we use the other principle, the value of the principal quantum number n of the valence shell. As the number of electrons increases in a many-electron atom, the ground state of the atom has electrons with higher values of quantum number n. These higher values of n affect two things, the size of the atom and the energy of the electrons. The higher the value of n, the larger the orbitals are that the outermost electrons occupy. This means that the atom gets bigger. This affects any property that has to do with the size of the atom. The size increases as we go down a column or group in the table. The higher the value of n, the higher the energy of the electrons in the orbitals. This affects any property that has to do with the energies of the electrons or changes in those energies, such as ionization energy and electron affinity. The energy of the orbitals increases as we go down a group. Let's look at the sizes of atoms. Measuring the size of an atom is not as simple as it might appear at first. Start with the fact that there is no clear-cut boundary to an atom, which means we cannot measure a single atom by itself. We can get around this problem by bringing two atoms of an element as close together as possible and measuring the distance between their nuclei, which are relatively easy to locate in space. The atomic radius is half that distance. There are complicating factors, however. Do the atoms bond when we bring them together, like oxygen, fluorine, and many others? If so, What we are really measuring is a bonding atomic radius. If there is no bond formed, like the noble gases, then we are measuring something different, perhaps a non-bonding atomic radius. What about metals? While they don't bond the way nonmetals do, there are attractions present. When we measure the distance between the nuclei, that is not really a bonding atomic radius. Given this caution, we can still talk about relative atomic radii of the atoms and how they change. As we go from left to right across a period, the atomic radius tends to decrease. While going from left to right in the same row, the value of n stays the same, but the nuclear charge increases. This results in more attraction for the electrons, pulling the electrons closer to the nucleus and decreasing the atomic radius. So the atomic radius increases from right to left across a period. As we go from top to bottom in a group, the atomic radius also increases. Going down a group, the effective nuclear charge stays the same, but the value of n increases. The larger value of n means a larger orbital, resulting in electrons that are further away from the nucleus and a larger atom. So the atomic radius increases going down a group. When we compare ions, the size of the ion depends on three things: the nuclear charge, the number of electrons, and the orbitals in which the electrons reside. We can compare ions in two ways. First, positive ions, the red hemispheres on the left, are smaller than their neutral atoms, the gray hemispheres on the left, because we have fewer electrons with the same number of protons, the same nuclear charge. This reduces the repulsions and allows the electrons to be pulled closer to the nucleus. For negative ions, the blue hemispheres on the right, they are larger than the neutral atom, the gray hemispheres on the right, because there are more electrons for the same nuclear charge. This increases the repulsions and pushes the electrons further away from the nucleus. This is the easy comparison. What happens when we compare one ion to another? First, ions within a group behave the same way as the neutral atoms do, increasing in size as we go down the group, and for exactly the same reason. The ions most commonly are the same charge, and so the ions will have the same effective nuclear charge, and the only variable is the size of n. The larger n gets, the larger the ion. When comparing ions across a row, we must exercise some care, because both the nuclear charge and the value of n may change. For example, take the sodium ion and the chloride ion, which are in the third row. For the sodium ion, Z is 11 and N is 2, because we have removed the 3s electron. The chloride ion has Z equals 17 and N equals 3, since we have filled up the 3p subshell. It is hard to judge whether the trend in atomic number or the trend in the principal quantum number is more important. However, there exists a comparison which simplifies all of this, even with ions of both types and in different rows. Since most of the common ions have a noble gas configuration, if we compare ions that have the same number of electrons, that is called an isoelectronic series, we find that there is only one thing changing, and that is the nuclear charge. Within an isoelectronic series, which may include the noble gas, a neutral atom, the size of the species decreases as the atomic number and the nuclear charge increases.